We continue presenting the calculus menu for wxMaxima, and we're going to start with calculating a maxima. It's a concept that I skipped last time, but basically it says, for example, if you're trying to find the maximum of a function here, it's equivalent to finding the minimum of the negative. And so we could go and say calculus find minimum and change to minus 1 minus x minus 2x squared. And when we do that, we find that the maximum occurs at this point. Okay, that's the one I had skipped. So let's get to, we already had get series. We had the Pede approximation. And so now we're going to calculate sum. This is just calculating a summation, and basically it's nothing complicated. You go calculus, calculate sum, write the expression for the sum 1 over k squared from k equal 1 to k equal 1 to infinity in this case. And when you get the result here, it gives you this simplified sum, and what you get is that this sum is equal to pi squared over 6. Now if you want to see what summation you're calculating, put the apostrophe before, and it shows that the summation is 1 over k squared. That's summations. And for products it's going to be similar, except that now you're calculating a product, and then you're going to get the function product, and the product of 1 over k from 1 over k equal 1 to 10 is equal to this one. And if you want to see the product that you calculated before it's evaluated, put an apostrophe and you're going to get this result. Laplace transform. This is a technology that is used in differential equations. Particularly we're going from time domain functions to the frequency domain function. So this expression here means the Laplace transform of the function f of t is equal to a certain function uppercase of f of s. The inverse function will be the inverse L to the minus 1 of the function in the frequency domain equal to the function in the time domain. You can find a lot of literature about the Laplace transform. I'm just going to show you here what calculus Laplace transform looks like. It simply means calculus Laplace transform, where you type the expression you want to find the transpose to, the old variable which is t, a new variable which is s, gives you the result called Laplace. And it says that the Laplace transform of sine of t is 1 over 1 plus s squared. The inverse Laplace transform, which is simply go to calculus, inverse Laplace transform, type the expression you want to find the inverse to, the old variable is s, the new variable is t, and you get this ILT, that means inverse Laplace transform. And it says it's equal to 1 times delta t plus t. This delta is what's called as the Dirac delta function, which is a concept used in control and signals and systems. Then I'm going to go quickly over this. The greatest common divisor is the greatest common divisor of a couple of polynomials, and in this case I use difference of cube, difference of square. It tells me that x minus 3 is the greatest common divisor that you can have for these two polynomials. You can also try it for numbers. The greatest common divisor of 27 and 6 is 3. The least common multiple, again I use x to the 4th polynomials. In this case is x minus 3, x plus 3, x squared minus 91. The least common multiple of, let's say, 45 and 15 is 45. Divide polynomials. This is the famous polynomial division. And basically when you activate these, you go calculus, divide polynomials, type in the polynomial in the numerator and type in the polynomial in the denominator, and say OK. For example, I'm dividing here this is fifth order polynomial by this second order polynomial. You get two terms. The first one is the quotient, and separated by the comma you get the residual. Okay. We can check here. No, actually that's it. That's all the division. The next example is in partial fractions, and actually what I did here, I created my own partial fraction. and simplify it. So in problems of integration with partial fraction, for example, you get something like this, and you want to find the partial fraction corresponding to that. So this was part of my preparing this document. You actually don't need it. And what I did here, I created a numerator polynomial and a denominator polynomials, and then I went for calculus partial fractions and say for n over d, with variable x being the reference, you get this command part frac n over d, and it gave me those partial fractions. Checking by using the rat simplification of the latest result, you do get that numerator and that denominator as I had over here. The final topic here is continued fractions, and continued fractions are fractions of the form a over 1 over b plus 1 over c. You're going to see something here. This is an when you do that, you go calculus continued fraction, and it refers to the previous result. So let me just enter a number here, 8.5662. It says you can approximate that number by these continued fractions. I haven't found any practical applications to them, but this is an approximation for pi, an approximation for e on partial fractions. Partial derivatives. There is a symbol of partial derivatives here, but it's non-functional. If you define a function of two variables using the colon equal, you just need to use the diff function to find those corresponding partial derivatives. There's no partial derivative symbol special. And when you use the apostrophe, you get the total derivative, even if the functions in here are of two variables. And then when you execute the derivatives, you get the result that would be correspond to the partial derivatives. So you can still use the diff command for partial derivatives. Here's another example for second derivatives. First with respect to y, then with respect to x. First with respect to x, then with respect to y. We're getting the same result, of course. Multiple integrals, you do integrate of integrate, you get a double integral. Here's one more complicated, but it already skipped the first integration. This quantity positive, yes, I get pi r squared. To illustrate this, I'm gonna copy these and do, oh, I'm missing a parenthesis here. And it gives me that result. It doesn't even give me the integration before the execution, even though I have a percentage. I'm sorry, a apostrophe. And so with that, I conclude my presentation in 3 parts of the calculus menus, and we're going to continue with other videos in the near future.